right, ladies and gents, our topic this evening is compound events and tree diagrams. Some of you have already gotten to compound events in your iReady lessons, and you might have learned a shortcut. That shortcut's wonderful. However, you also have to be able to solve compound events with tree diagrams. So our objective is I know what compound probability is, and I can calculate the probability of compound events using a tree diagram and organized list. There will be some questions on your unit test where you have to make a tree diagram and you have to use an organized list to answer the question. So what is compound probability? Some of you remember maybe from your early elementary days of language arts class learning about compound words. And a compound word is simply two words put together. So backpack, those are two separate words, and you put them together and you get backpack. Compound probability is kind of like that. It's the probability of multiple events happening. So you have one event, maybe the probability of rolling a 3, and you put that right next to another event, the probability of landing on heads, okay? So example, rolling a 3 on a die and then rolling a 3 again. That would be compound probability because, whoopsie, there are two separate things that are happening. Spinning a spinner and landing on green, and then flipping a coin and landing on heads. Another example, two events, and it can be more than two. It could be spinning a spinner, landing on green, flipping a coin, landing on heads, and getting a 2 when you roll a die. Also, pulling an ace of hearts from a deck of cards, and then pulling any club from the deck of cards. These are all different kinds of compound events that you need to be familiar with for this unit. It is more difficult to calculate compound probability than it is to calculate simple probability. I get a lot of people that try and solve these compound probability things the same way you would solve simple probability, and it simply doesn't work. You can't just intuitively or automatically know what the probability is of these compound events. And a lot of people kind of answer quickly and move on, and that causes problems for you. Let's take, for example, simple probability. We have the probability of rolling a 6 on dice, okay? You have one die, you roll it, you get a 6. That is a 1 in 6 chance. That's very straightforward. There's 1 6 on the die, right? And there are 6 sides. So it's 1 over 6. Compound probability is not as easy. You've got let's say you want to roll a 6 and then you want to roll a 2. Some of you might say, oh, well, maybe that's 1 out of 12 because you're rolling the die twice, and so you have 12 things there. Some people might want to do, oh gosh, I don't know, 8 out of 6. They'll say 6 plus 2 is 8. Or they'll try and simply say, well, it's 2 out of 6 because you can get a 6 or a 2. None of those work. The actual compound probability of rolling a 6 and then a 2 is 1 out of 36. And this is actually one of the more simple compound probabilities. So you can't rely on just, oh, I know how to do it. It's this. You have to take your times and work through the steps like a tree diagram and an organized list in order to really make sure you get the answer correct. So let's talk about these tree diagrams and organized lists. This is just one way to approach compound probability. Tomorrow we're going to do compound probability with tables, and then we're going to look at something called the fundamental counting principle that's going to help us understand that as well. But for tree diagrams and organized list, the combination of a tree diagram and an organized list is powerful. A tree diagram by itself is not useful. It's too easy to get confused, to get disorganized. An organized list by itself is not useful. It's too easy to miss an outcome. However, when you combine it, it's like magic. It is awesome and very useful. All right? You can solve almost any OAA question, I should add, on probability, or test question simply by using tree diagrams and organized lists. There is a shortcut, and I'm not telling you yet. And if you know it, you don't get to use it yet because I need to make sure you understand these more concrete examples before we move to the shortcut, which is like abstract, more algebraic. So downsides of tree diagrams and organized lists. It can take a while. It's not the fastest thing in the world. And all outcomes must be equally likely. For example, on a die, all 6 of the sides have an equal chance of being landed on. As opposed to, let's say you have a little cup, right? And you're going to throw the cup in the air. The cup can land on its side. The cup can land facing up. The cup can land facing down. All those are different ways, and they're not equally likely. So this situation is no good for organized lists and tree diagrams. Let's work through an example. If I have a spinner here, and I want to find the probability, P parentheses, of getting orange and then green, we have to make a tree diagram for this at this point. So we want to know the probability of spinning the spinner and landing on orange, and then landing on green second. So let's start out with the first spin. And let's think about the different options we have for the first spin. If I spin this spinner, it can either land on blue, green, or orange, right? That is my first level of the tree diagram. It is my first spin. And actually on tree diagrams, I encourage you to abbreviate it. So you could even just put B, G, oh, golly, sorry, hit the button. B, G, and O. Then you have to deal with the second spin. Second spin. And the reason this is called a tree diagram is because you're going to have little branches coming off from each of these letters in the first level. So you can spin it on, you can land on blue the first time, and then on the second spin, you could land again on blue, or on green, or on orange. If you landed on green first time, the second spin, you could land on blue, or green, or orange. And if you landed on orange the first time, you could land on blue, green, or orange. So this tree diagram shows all the different possibilities: blue, 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 green, blue, orange, etc. So the first level is the first event. The second level is the second event, and you use these branches to connect the levels. So the next part of this is making an organized list, taking the results from your tree diagram and making an organized list to show all of the possible outcomes in the situation. It is extremely important to keep your work neat and organized, as it's really easy to make a silly mistake. It's really easy to miss one of your outcomes. So if I'm making my list, let's start with my blue for my first spin. I can do blue on the first spin, blue on the second spin. I can do blue and then green, or I can do blue and then orange. So for my organized lists, I'm going to do this: blue and then blue, blue and then green, blue and then orange. I can also land on green first and get green and then blue, green and then green, or green and then orange. Green, blue, green, 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 orange. And lastly, I can get orange, blue, orange, green, or orange, orange. Orange, blue, orange, green, orange, orange. Something I want you to notice about this is in my organized lists, I have 9 possible outcomes. 1, 2, 3, 4, 5, 6, 7, 8, 9. If you look at your tree diagram, this is where a lot of people make a mistake on the tree diagram. A lot of people will say, okay, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 outcomes. There are not 12 outcomes. This first row does not count. It's only your final row that tells you how many outcomes there are. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's because this final row shows the final path. So blue to blue, blue to green, blue to orange. So I have 9 different outcomes here. That means any probability I have is going to be out of 9. And my original question asked me to find the probability of getting orange and then green. So I have to see which one of my results is orange and then green. The only one that is right here. This one doesn't count because this is green and then orange. That's very different than orange and then green. So I have a 1 in 9 chance of spinning an orange and then spinning a green. That is my final probability. Of course, you always want to make sure it can be simplified, but in this case, it can't. All right, so your reflection is create a tree diagram and an organized list to determine the probability of spinning the following spinner and landing on blue, then flipping the coin and landing on heads. So we're looking for the probability of blue, then heads. If I don't see the work in your notes tomorrow, it doesn't count. I will be checking, okay? So, best of luck. Can't wait to see what you guys come up with. Have a good night.